One of the important concepts in signal analysis is the sampling. So we usually do the discrete Fourier transform. For that we do the sampling. What is actually sampling and why you need it? Say this is our sinusoidal signal. This is continuous signal. When we will do the FFT in MATLAB, actually we don't take all the points. We take the sampling. So, and also to reconstruct the data, we don't need all the points. Say if we get that this point, say this point, like this point, or some other points like this, then we will be able to reconstruct the sinusoidal signal. By seeing these, all these points, we will be able to reconstruct the sinusoidal signal. But there is a limitation that how much points we need to take. So there is a theory of called the Nyquist sampling theorem, or the Nyquist Shannon sampling theorem. It tells that, say if your time domain signal frequency is f, then at least you need to sample, at least minimum size of the sampling should be 2f at this rate. If you don't do that, then there will be a sampling error, there will be aliasing. So at least you need twice the rate of your time domain signal. Say now for our case, say we want to analyze these data. This is a sinusoidal signal. We have the two sinusoidal signal here, one with 50 Hz, another with 220 Hz. So if you want to do sampling here, our sampling rate should be at least greater than 220, the twice of 220. Say here we are setting the sampling rate of sampling frequency of this analysis equal to 2000, and our data length, time domain data length is 1000. You can set any data length. So when we'll do the FFT, usually FFT will be faster if you do the total number of FFT points is power of 2 to the power n, power of 2. So we are calculating the next index of n for the length of 1000. Actually we want 2 to the power 10 equal to 1024, kind of like we want to find the next point. So this will give us 1024 points, and we want to do row wise data. See here, this is the FFT. We are doing the time domain signal, and then total how many number of points we want to do up to 1024, and then the dimension is 2. Now one thing to note is that although our time domain signal has 1000 points, and when we are doing FFT we are using 1024 points. So what about the points from 1001 to 1024? So the FFT will automatically add or append 0 from 1001 to 1024 to make it faster. That's called zero padding. So if we do the FFT, we will find the y. And now one thing to note is, let's run this program, that if we do the FFT, we will find this kind of signal. The left side, left to peak, is for the real portion of the FFT, and the right portion is the imaginary portion of the FFT. Now one thing that's we make mistake is to understand. So here, although we have 50 Hz frequency of sinusoidal signal as well as 220 Hz sinusoidal phase signal, but what do you see here? Here we see 27. What do you see here? We see 114. And in the x-axis is the total number of points. So total number of points in our case is 1024, and in y-axis is the amplitude. So now thing is that how can we tell in the x-axis is the frequency? Instead of points, we want to make the x-axis as a frequency. So how can we do that? So there is a relation between the x-axis point with our sampling frequency. So here is how can we convert? So here is 27. Say if we have, say in our case sampling frequency is say 2000. Now what is the total number of points? In our case after FFT, total number of points is 1024. So if I divide 1024, so here in x-axis actually 1 points correspond to 1.95 Hz of frequency. So here is 27 point, right? So remember that first point is corresponding to 0. So here the first point starts from 1. So 27 actually becomes 20, total usable point is 26. If you multiply it 26, so this is 50 Hz. What about another point here? Say 114. Now same thing, 2000 Hz divided by 1024, we will find that this multiply 113, which is equivalent to 220. So this is the way that how you will find the actual frequency. So we can calculate like this. Say that to convert this, so I'm taking the half portion of that, and the frequency is Fs divided by n, total number of points, and this is just matrix usually. So simply Fs divided by whatever total number of points after Fourier transform, that corresponds to 1 point, and you have to start from 0 because you have 0 frequency at the DC point. Then if I go in the next thing, we will see here that we are actually getting whatever we calculate. So 50.78, here is 220.7 that we calculated using calculator. So 220.7 Hz, that's the frequency. Let's just for clarification further, let's do one thing. Let's change this frequency to 3000 sampling frequency. Let's see how does our calculation goes. So here if you use 3000, so let's see we can see the right frequency or not. So this is before calculating anything. So what are the things we are finding here? So before calculating anything, we see that here we are trying to see the point is 18, right? So if you use a calculator again to calculate, so 3000 was our sampling frequency, total number of data points was 1024, is like that. So now the x-axis, in x-axis 1 points correspond to 2.929 Hz. So that's different from previous one. Previously when our sampling frequency was 2000, that time each points correspond to 1.95 Hz. So it depends what is your sampling frequency. Multiplied 17 because first point is the DC point, you have to ignore that. So this is again 49.8 or equal to 50. If we see here 49.8. Actually it depends what is your sampling frequency. Like based on the sampling frequency you can reach how much, or you can reach nearest to 50 Hz. So that's why you have to be careful. So these are the signal, we know that what is the frequency here, say 50 Hz or 220 Hz. So we just simply calculate it, we just simply set the sampling frequency. But in real time, say in real example or real data analysis, you have to figure out what is the sampling rate, and you have to make sure that your sampling rate should be higher than twice of the maximum frequency of your time domain signal, because you have to follow the Nyquist Shannon sampling theorem. Otherwise, you cannot be able to regenerate, or you cannot be able to gain again the time domain signal after FFT.